The logic for building tall seems simple. To go higher, you just need to be stronger. Use more steel, pour more concrete. But at extreme scales, this logic collapses. The very materials that provide the strength, the millions of tons of concrete and steel, become the building's greatest threat. Every super tall skyscraper is in a relentless battle, not just with the forces of wind and weather, but with the crushing, inescapable pull of its own gravity. This creates a chain reaction of engineering challenges, and the first link isn't in the sky, it's deep in the earth, where the ground itself strains under a load it was never meant to support. So this isn't a question of money, it's a question of physics. How far can humanity push before the laws of nature simply say no? The first link in this chain of limits is the ground beneath our feet. Think of a skyscraper's foundation like a person standing on soft sand. If you stand normally, your weight is distributed, and you sink slowly. If you stand on your tiptoes, the same weight is focused on a tiny point, and you sink immediately. That is the essence of ground pressure. A super tall skyscraper is the ultimate example of this. An object weighing hundreds of thousands of tons trying to stand on its tiptoes. The Burj Khalifa, for example, weighs around 500,000 tons. The immediate engineering problem wasn't how to build it up, but how to stop it from sinking down. And it was built on some of the worst possible ground for such a project, a mix of soft marine sediments and weak, sandy soil. There was no solid bedrock nearby to anchor to. By all conventional logic, building the world's tallest structure here was impossible. The ground would simply give way, causing the tower to tilt or sink like a modern-day Leaning Tower of Pisa, but on a catastrophic scale. So, how is it standing? The answer is an incredible feat of engineering hidden entirely underground. The tower rests on a massive, three-winged concrete foundation, but this foundation doesn't just sit on the weak soil. It is connected to 192 enormous concrete piles, each 1.5 meters in diameter, drilled nearly 50 meters deep into the ground. But here is the critical detail. These piles don't rest on a hard bottom. They are what engineers call friction piles. Instead of transferring the building's immense weight to a single point of bedrock, they transfer it along their entire length through the force of friction. The rough surface of the piles creates an immense grip on the surrounding soil and sand. In effect, the engineers didn't fight the weak ground, they recruited it. They turned a massive volume of the earth itself into part of the foundation, making the ground hold the building up by grabbing onto it from all sides. It's a structure held in place not by solid support, but by a calculated, immense, and invisible grip. So, engineers found a way to stop the building from sinking into the earth. They solved the vertical problem, but in doing so, they created a new one. By building so high, they turned the skyscraper into a giant sail, exposing it to a powerful and relentless force that doesn't push down, but sideways. The battle against gravity was just the beginning. The war against the wind was next. Having anchored the tower to the earth, engineers now had to confront an enemy that couldn't be held down, the sky itself. At extreme heights, wind is not just a force, it's a dynamic, turbulent river. And a super tall skyscraper is a slender reed planted in the middle of it. The common assumption is that a building must be rigid to resist this force, but the opposite is true. A super tall must be flexible. It must sway. The real danger isn't the push of the wind, but its rhythm. This phenomenon is called vortex shedding. As wind flows past a tall cylindrical object, it creates alternating low-pressure zones, or vortices, on either side. These vortices pull the structure back and forth, creating a vibration. If the wind speed is just right, its rhythm can match the building's natural frequency of swaying. This is called resonance. It's the same principle as pushing a swing. Small, timed pushes can create a huge, uncontrollable arc. For a skyscraper, resonance is a catastrophic threat. A steady breeze could, in theory, amplify the tower's sway until it literally tears itself apart. This is why the Burj Khalifa doesn't look like a simple, smooth tower. Its shape is its primary defense. The building's cross-section changes at different heights, with a series of steps and setbacks. This is not an aesthetic choice. It's a strategic act of aerodynamic sabotage. These irregularities confuse the wind. They prevent the formation of a single, powerful, organized rhythm of vortices along the building's height. The wind tries to play the tower like an instrument, but the tower is intentionally out of tune with itself. But even this brilliant design isn't enough. For added protection, many supertalls employ a second line of defense, deep inside the structure, a tuned mass damper. The most famous example is inside Taipei 101, a colossal 728-ton steel sphere suspended by cables near the top of the tower. It's a giant pendulum. When the wind pushes the building one way, the massive sphere swings in the opposite direction, acting as a counterweight. It absorbs the wind's energy and cancels out the vibrations, calming the building's sway from the inside. So, the engineers solved the problem of the ground, and they devised brilliant strategies to outwit the wind. They created a structure that won't sink and won't be knocked down, a triumph of stability. But a building is not just a monument to be looked at, it's a space for people. And in solving the physics of stability, they created a new, immense logistical challenge. Now that you've built it, how do you get anyone to the top? The answer is not as simple as just using a longer cable. The tower is stable, it won't sink into the ground, and it won't be torn apart by the wind. But a skyscraper is not a statue, it's a vertical city. And now, engineers face a problem that seems almost trivial by comparison, yet it presents one of the hardest limits of all, getting people to the top. The obstacle isn't speed or power, it's the simple, brutal weight of a steel cable. There is a fundamental physical barrier for conventional elevators. A steel rope can only be so long before it can no longer support its own weight. The exact practical limit is debated, but it's generally understood to be around 500 to 600 meters. Beyond that point, the cable's own mass becomes so immense that there is almost no capacity left to lift a cabin, let alone the people inside it. The intuitive solution, just use a stronger, thicker cable, doesn't work. A thicker cable is a heavier cable, which only makes the problem worse. You are defeated by the very material you are using for strength. It's a hard wall imposed by gravity and the limits of material science. So how does the Burj Khalifa, a tower stretching over 800 meters into the sky, have elevators at all? It doesn't solve the problem. It cleverly bypasses it. No single elevator journey goes from the ground floor to the top. Instead, the building operates like a vertical transport network. Passengers take one of the world's fastest express elevators to a sky lobby, a transfer station high in the tower. From there, they switch to a different set of local elevators that serve the upper floors. This solution, while functional, is a major compromise. It's inefficient, forcing residents and workers to change elevators midway through their journey. More critically, it is incredibly expensive in terms of space. The sky lobbies and the multiple redundant elevator shafts they require consume thousands of square meters of prime real estate, space that cannot be sold or rented. This workaround is a constant, concrete reminder of the invisible barrier that still dictates vertical construction. To truly break this limit, some engineers argue we must eliminate the rope entirely. The next frontier is ropeless elevator systems, which operate more like trains running vertically inside a building's walls. Using magnetic levitation, multiple cabins could travel up and down in the same shaft, and even move horizontally to get out of each other's way. This would not only shatter the 500-meter height barrier, but would transform how we design and use tall buildings. But for now, this remains a technology of the future. So, let's assume we solve the elevator problem with sky lobbies or new magnetic systems. The building is stable, and we can get to the top. The structure is safe. But is it habitable? We've conquered the physics of stability and logistics, but now we face the most sensitive and unpredictable limit of all, the human body and mind. The tower is stable, the elevators are running. We've conquered the raw forces of physics, but in doing so, we arrive at the most sensitive and unpredictable limit of all, the human being. A building isn't just safe on paper, it must feel safe, and it must be comfortable. At the top of a super tall skyscraper, both of these things are under constant assault. Even with the most sophisticated dampers, the building still sways. It's a slow, powerful, and relentless motion. On the highest floors, This movement, while perfectly safe from an engineering perspective, can become a source of profound discomfort. Occupants can experience a subtle form of motion sickness, similar to being on a ship at sea. Water in toilets or bathtubs can be seen sloshing. The building itself groans and creaks as its structure flexes, creating an unsettling soundscape. This is a biological limit. The top floors, the most expensive real estate with the best views, can become the least pleasant places to be. Then there is the issue of safety. What happens if there's a fire on the 140th floor? The idea of thousands of people descending over 100 flights of stairs is not a viable evacuation plan. It's a recipe for disaster. The real solution is a concept that goes against all our instincts. You don't evacuate down, you evacuate sideways. Modern supertalls are designed with refuge floors, entire levels of the building that are heavily reinforced, fireproof, and have their own independent air supply. In an emergency, occupants move horizontally into these pressurized safe rooms to wait for help. It's an ingenious solution, but it's another massive compromise, consuming entire floors of valuable space that can never be sold. And here, every one of these solutions, the friction piles, the aerodynamic shape, the mass damper, the sky lobbies, the refuge floors, comes together to form the final and perhaps most insurmountable barrier: economics. Each physical problem we solve adds an immense cost and consumes non-rentable space. The cost per square meter doesn't increase linearly with height, it increases exponentially. The building becomes a victim of its own success, where the very systems needed to make it stand and function make it financially unviable. This economic wall is the quiet, invisible force that stops most supertall projects long before they are ever announced. We have a chain of limits: the ground, the wind, the elevators, and the human body, all wrapped in a final, suffocating layer of cost. It seems that for every meter we build up, we must pay an exponentially higher price in complexity and compromise. So, is this the end? Are we doomed to forever inch our way up, fighting a losing battle against physics and finance? Or have we been asking the wrong question all along? This chain of limits, ground, wind, elevators, human comfort, all bound by the suffocating logic of economics, seems to paint a clear picture. We are approaching a hard ceiling. To see what happens when we try to smash through that ceiling with brute force, we don't need to look at a real project, but at a thought experiment, a conceptual design from the 1990s called the Exceed 4000. It was a proposal for a structure 4 kilometers high, nearly 5 times taller than the Burj Khalifa. But to support such a height using conventional steel and concrete, it couldn't be a slender tower. It would require a base 6 kilometers wide. It wouldn't be a building, it would be a man-made mountain, housing up to 1 million people, with its own internal weather systems. The Exceed 4000 wasn't a serious proposal for construction. It was a stark illustration of a dead end. It proved that the just build stronger philosophy, when taken to its extreme, leads not to a taller skyscraper, but to an absurdity of scale and cost that defies all reason. So, if fighting gravity with more mass is a losing battle, perhaps the real path forward is to cheat. The future of supertall construction may not lie in getting stronger, but in getting lighter. The greatest enemy of a skyscraper is its own weight. What if we could drastically reduce it? This is where the next revolution is taking place, in materials science. Researchers are developing carbon composites and other advanced materials that are many times stronger than steel, but a fraction of the weight. Imagine a skyscraper built not with millions of tons of concrete and steel, but with a lightweight, ultra-strong composite skeleton. Suddenly, the entire chain of limits begins to weaken. A lighter building puts far less stress on the foundation, opening up possibilities for construction on less than perfect ground. A lighter structure is less susceptible to the forces of its own inertia when swaying in the wind. And most critically, it could shatter the elevator barrier. A cable made from a carbon-based material could be strong enough to run for 1 kilometer or more without snapping under its own weight, making single-trip elevators to the top of a mile-high tower a real possibility. This shift in materials also inspires a shift in thinking about structure itself. For millennia, we have built through compression, by stacking things on top of each other. But this is an inefficient way to fight gravity. A far more efficient way is tension, hanging things. Some architectural concepts explore a future where, instead of a central core supporting the floors are hung from a massive external superstructure. These tensile structures are inherently lighter and stronger, distributing loads in a way that works with gravity, not against it. The ultimate limit to how high we can build, then, is not a fixed number of meters. It is a moving target, defined by the weakest link in a long chain of interconnected problems. For decades, that weak link was our understanding of wind. Today, it's a mix of logistics, economics, and materials science. The future of architecture isn't just about building higher, but about finding a fundamentally new way to build. The challenge is no longer to simply defy gravity, but to rewrite the rules of the game. The race to the sky continues, not on the construction site, but in the laboratory.